Right, okay. Hello, everyone. So welcome to walkthrough of what to do for Coordinated Science Paper 6, the alternative to practical. We're going to go through last year's May-June 2021 paper. So first off, just a reminder, all the basic stuff you probably know already. Make sure you put your full name here. You're gonna have to excuse my terrible handwriting. I'm getting used to my graphics tablet again. The center number, that's the school code essentially. And for us, that's the one that starts with MX and then 3 different zeros. And the candidate number, that's the 4-digit code or the 4-digit number that's for you. Okay, so just make sure you've got those there. You'll be given time to read through all of the papers, but first make sure that it is the correct paper. So all of you will be taking paper 6, alternative to practical, like this. Okay, so just make sure it says paper 6. It's not being mixed up with anything else. You need to answer all the questions on the paper, and you don't need any additional material. So you don't need any answer booklets or things like that. Make sure you read through all the questions. You need to answer all the questions. You need to use black or a dark blue pen, and you are allowed to use an HB pencil for any diagrams or graphs. That should say you must use an HB pencil for diagrams and graphs. Write your name, center number, candidate number in the box at the top. Write an answer to each question in the space provided. Do not use an erasable pen or correction fluid, so don't use whiteout. Just put a neat line through anything that you don't want marked like that, okay? Don't write on any barcodes. You're allowed to use a calculator. Make sure you're familiar with how your calculator works, and you should show all your working out and use appropriate units. That's really important because remember, if you get the answer incorrect, but your method was correct, you may get a mark there, okay? Other information, the total mark for the paper is out of 60, and the number of marks for each question is shown in brackets. Remember, coordinated science is a mixture of biology, chemistry, and physics. So I'm going to just go through the physics part of this. That will be 20 marks in total. Now, what happens sometimes is that there's 6 questions, each worth 10 marks each, or there'll be about 6 or so questions in total, and there'll be a difference in total marks, but the total marks for each section would add up to 20 for each subject, essentially. Sometimes it goes biology, chemistry, physics, biology, chemistry, physics. What they've done this year, or sorry, what they've done in last year is that they've gone through biology, then chemistry, then physics. The physics questions are at the end. Remember, you don't have to answer them in any particular order. So I would advise you take a minute to look through the paper at the start of the exam and look at which ones are the easiest or you find the most easy to do. That will give you a big confidence boost going into it, okay? Also, it means if you've run out of time, you've answered the questions that you're able to answer. And remember, physics sometimes goes at the end. So let's look through this here. So I can see here, if I go through the paper, I can see question 1 is something about movement of colored water in a celery stem. So that's obviously a biology question. If I scroll down here, you can see there's some graph work and things like that. Again, we're not going to do that because we're just going over the physics one. Again, student test some celery for nutrient content. Again, so food tests and things like that. Again, biology. We're just focusing on the physics now. Investigation. Student decides distinguish between sodium hydrogen carbonate and sodium carbonate. Again, this looks like chemistry. So again, in the real exam, you would answer this, but I'm just going to go through here. Student investigates surface area of reaction marble chips and hydrochloric acid. Again, it's chemistry. So we're just going to focus on the physics one here. Pure water has a fixed boiling temperature of 100 degrees C. Impurities such as salt. This is a chemistry question, and it's a design and experiment question. Okay, so we're going to go here to question 6. Question 6 is a physics question, and so is question 7. So if you feel comfortable answering the physics one first, go ahead and do the physics ones first. What I would suggest you do is with the physics ones as well, it's a lot easier, I would say, than biology and chemistry, because a lot of it is just sort of practical work that either you've seen in class or that you can use your common sense with. We don't have to remember things like what food tests are used, how do we test for certain chemicals and things like that. We just need to use a certain set of skills. And those skills are transferable pretty much across all different types of the experiments. Also, you'll see here in a second, you don't need to remember the formula for any physics concepts that are being used. The most important thing is that you are reading through the entire question. There is a huge temptation when you get to any paper 6 question to ignore all of this and jump straight to the question. Take a minute to read through the question. Okay, remember you've got an hour and a half, so that's about 12.5 minutes per question. Okay, so you've got plenty of time. So let me just first make this a little bit easier to read, and let's make it a nicer color. There we go. So let's read through this. A student investigates how the potential difference V across a lamp and the power P of the lamp change as the length L of a resistance wire in series with the lamp changes. The student sets up the circuit as shown in figure 6.1. So I'm going to label the circuit now. You won't need to do this, but I think it's important that we label it so we know what's going on. You won't be asked to do this unless they specifically say label this part of the circuit diagram. So what we've got here is an open switch. So essentially the circuit is off right now. It's in like its off mode. Okay, so no current is flowing. We have 2 cells here. So this is our battery. Okay, the cross there, that's our bulb. That's our light bulb. And then across it, in parallel, we have our voltmeter. And then we have our ammeter. And so remember, a voltmeter always goes in parallel with the thing you want to measure the voltage across it. And an ammeter goes in series, so it's connected in a chain. So we've got our circuit here like this. And what's going to happen is current is going to flow through the bulb, flow through this wire here. It's going to flow through the wire here until it reaches the sliding contact. And then the current is going to flow up along here and then through the switch when it's closed. Okay, so that's what we've got there. Let's look at the procedure. So the student closes the switch. So I'll just make a note of that. So the student has closed the switch now. So the circuit is closed. That means current is now flowing through it. They place the sliding contact S on the resistance wire at a distance of 15 centimeters from X. So the length from here to here is 15.0 centimeters. They measure the current I flowing through the lamp using the ammeter. And remember as well, I is the symbol for electrical current. A is the unit. Okay, A is the unit. Okay. They measure the potential difference V across the lamp and record it using the voltmeter, and then they open the switch. So again, they've opened the switch, they've turned off the circuit. The readings on the ammeter and the voltmeter are shown in figure 6.2. So we've got an analog voltmeter, so a needle, and an analog ammeter. Okay. And I think I can see where this is going, but I'm not going to presume anything. I'm going to look through here, and the first part of the question, it says here, record in table 6.1. So here, the current I and the potential difference V for 15 centimeters for the length of the wire. Okay, it's 2 marks. So that means you're going to get a mark for each correct writing, for each correct reading here. So let's do the current first. I'm going to zoom in for the current one. So let's just get a little larger there. Okay. So we can see the ammeter goes up. There's an interval here that's not marked, and then it's 0.2. And then there's an interval that's not marked, like a medium little notch there, and it's 0.4. So what that's telling me is that this here is 0.1, 0.2. This is going to be, sorry, that little notch there is going to be, let's do that properly. That little notch right in the middle is 0.3, and so on. And so we've got 5 scale divisions. So we go from 0.2 to 0.3 in 5 scale divisions. So that means that each little scale division is worth 0.02 of an ampere. So where the needle is pointing is the second one. So it's going to be 0.2. We already measured 0.2 there. And then it's going to go up by 0.02, and another 0.02. So it's going to be 0.24 amperes. And so we're going to record that in our table now. So if we just scroll down, we're going to record that in our table. Our current is 0.24. I don't put the units because the units are already in the table. Okay, and one thing I will need to do as well is I need to make sure that the decimal places, or the significant figures, I should say, are the same across. So I can see here they're all to 2 decimal places, so this is appropriate. If I had a greater number here, I'd have to round it to 2 significant figures here. So let's do the potential difference. So again, the potential difference, we're going to use this one here. Potential difference. Now in this case, the scale is slightly larger, so we've got 1, 2, and 3, and so that means each of these ones, if I count them, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, it goes up by 0.1 each time. So here, I can use that as a guide. That's 2.5, the middle bit, and this bit where it's pointing to is 2.6. So it is 2.6 volts. And again, I can see it's 1 decimal place, so I'm just going to write 2.6. No units. If you write the units, you could lose a mark because the units are in the column heading. Okay, so that is our first 2 marks out of 10. Remember that this is just reading off a graph. That is 2 marks out of the 20 for physics. That's 10% of the physics marks there. Okay, so now it says suggest why the student opens the switch before taking readings. So what they're saying is, why does the student turn the circuit off between each reading? Why do they turn the circuit off between each reading? There's a few reasons here. Now, the most reasonable one, I would say, is that the cells or the battery will run down. If you leave them on too long, the cells or the battery would run down. So we'll say that there. So we can just say cells or battery will run down. There we go, and that's our other mark, like so. Okay, now the student repeats the procedure for A for values of length equals 30.0 centimeters, 45.0 centimeters, and 60.0 centimeters. The results are shown in table 6.1. So we've got our values there. Calculate the power P of the lamp for 15 centimeters length of wire. Use the equation shown. Okay, so use the equation shown. Record your table in 6.1 and your value of P to an appropriate number of significant figures. Okay, so first off, we'll do this here. We're going to do P equals V times I. So in this case, P is going to equal V times I. So that's V is 2.6 times I 0.24. So P is going to equal, I'll just grab a calculator from the bag. So 2.6 times 0.24 or 0.24, and that equals 0.624. So I'm going to put that in my table, 0.624, but there's a problem. These are I've got the answer correct, but I need to make sure that it's to the same number of significant figures. So in this case, I actually am going to round this to 2 significant figures. So this is 4, so this rounds down to 0.62. Again, if it was 5 or greater, it would round up. So I'm keeping it to the same number of significant figures. So I would get a mark for the correct answer, and I would get a mark for the correct number of significant figures. So if you put 0.624 in the table, you would get 1 mark, but if you put 0.62, you get your 2 marks, okay? So that's 5 marks already out of 10 for this question, 5 marks out of 20 for the full lot of question. Then it says here, complete the column heading in table 6.1 by giving the unit for power. So this is the only thing you have to remember. To remember that the unit for power is watts. So you just put watt there in the dotted line. That's always a clue in your table. If you see those little dotted lines there underneath, that's a clue that you're going to have to write something in it. Okay. Now, what I would do is I would make sure you write it underneath, but I can't quite write very well with this tablet. So just make sure you write it like the W is sat on the top of those dotted lines, so it's nice and clear. I can't imagine an examiner marking you down if you didn't, but we want to keep everything nice and neat just to keep the examiner happy so that they want us, or they want to look for marks for us. So that's our other mark there. So now we're at 6 marks for this question. State how, so for question part 3, state how the results in table 6.1 show that the brightness of the lamp decreases as the length of L of resistance wire increases. Okay, so for this one, we just need to state something. It doesn't say, we just need to say what's happening, not why it's happening. So what we would say is we just need to say that current or electrical current, or we could electrical current, or we could say voltage or potential difference. Or we could say power decreases, so all of them decrease as length increases. So we don't need to say why it's happening, and you just need to say one of these things. So you could say current decreases as length increases. You could say potential difference decreases as length increases. You just need to say one of those factors. You would get a mark for any of those. So there we go, that's our other mark. So another one here is another student. Another student suggests that the potential difference V across the lamp is proportional to the length of resistance wire in the current. State if the values in table 6.1 support this suggestion. Justify your statement by referring to the values. That's really important. You've got to refer to the values. So you would say it's not true or not supported. True or supported. You need to say why it's not true, and then you would say because. So it's not true because, what you would say is, it's not true because if something is inversely proportional, oh, sorry, it's proportional to the, sorry, it's not true because L divided by V is not consistent or not, is not constant. So if that relationship was true, L divided by V would not be constant. I would say that's the hardest part of the question, and it's only worth 1 mark. Okay, you need to say your statement and why. Okay, so then the student decides to repeat the investigation, but she replaces the resistance wire with a variable resistor. So we've got to remember the circuit symbol for variable resistor. Complete the circuit diagram in figure 6.3 to show how the variable resistor and voltmeter are connected so that the lamp and the potential difference across the lamp can be varied. Now, the first thing I would say here is you've got to use a ruler for drawing any wires and things like that. Okay, so first thing is we want to measure the potential difference across the lamp and how that can be varied. So first off, let's draw our circuit for potential difference. So we'll draw our little circuit there. That's going to be our voltmeter. So we're going to get a mark for drawing our voltmeter properly. So a circle there. And then also we need to make sure we're drawing it properly. We need to write V for voltmeter, like so. That's going to be our full marks there. Let's make that a little bit neater. Like so. There we go, like so. Okay, so we get our voltmeter there like that. That's our first mark. So it's our first mark, voltmeter correctly placed in parallel, and we've drawn the circuit correctly. Then we need to have, if we're going to vary the current across here, we need to have a variable resistor. So the first thing we're going to do is draw our symbol for variable resistor. So it's going to look something like this, with a line through it here like this. That's our variable resistor, or that's our circuit symbol for variable resistor. And in order for this to work, it needs to be in series with the light bulb, or with the lamp. So we're going to just make it, extend it as part of a chain here, like so. And we need to complete the circuit as well. So we need to have clear, nice lines there like this. Complete circuit, nice, neat lines. And we're going to use a pencil for this as well. Reason being is if you made a mistake in pen, it's going to be a real pain to draw it out. So your second mark is for a correct circuit symbol for the variable resistor. Remember, it's a resistor with an arrow through it because that shows variable resistor. Voltmeter across the lamp because we're measuring the potential difference across the lamp. And again, drawn properly, correct circuit symbol. 1 mark for each, that's your 2 marks. There you go, that's 10 marks, 10 out of 10 marks. Now I would say that's pretty fair. The hardest question I would say was this last one. Remember, that's only 1 mark. Okay, so let's go to the second question, so the last question. Student uses a spring to measure the mass and the density of a stone. Figure 7.1 shows a full-size diagram of the spring. So that's your clue here. This diagram means that they're going to want us to measure something about the diagram. Now, it can either be a full-size diagram in the exam, or sometimes it's a diagram that's to scale. So you would say that the diagram here is 1/10 the size of the actual equipment, and then you would scale up your measurements. So what we're actually going to do is take a ruler and measure something about this. But let's read through the rest of the question. It says here, measure the length and record L0 of the unstretched spring in centimeters to the nearest millimeter. So literally you are measuring from here to the nearest millimeter. Okay, so in this case, to the nearest millimeter, you would literally get your ruler out and obviously can't do it here, but over from here to here, you would measure this length on the piece of paper with a ruler. Okay, a lot of people always think, well, I've just got to do that. That's all I've got to do. Yes. Now, obviously, I can't do this on a screen right now because I've been zooming in and out. So I'm just going to look at the mark scheme. But if I was to measure this out properly, if it was printed to scale, I would find that it is 5.5 centimeters. And that is to, remember, 0.1 of a centimeter is a millimeter. That is to the nearest millimeter. Okay, and that's our mark. Literally just that. I guarantee you will have either that or reading a temperature off a picture or a diagram of a thermometer. A lot of people are like, well, is that all I've got to do? Yes, but just make sure you include the units and that you do it to the precision that they've stated. So in this case, do it to the nearest millimeter. If, for example, I rounded this up and said, oh, it's 6 centimeters, it is not, because that is not to the nearest millimeter. That is incorrect. Okay, right. So let's keep going. So we've got here, the student sets up the spring in a clamp, as shown in figure 7.2. And the procedure is the student suspends a mass of M of 200 grams on the spring. The student measures the new length, which is going to be LM of the spring in centimeters to the nearest millimeter. The results are shown. So she has recorded this now, or they have recorded this now, and it's 13.7 centimeters. Calculate the extension E of the spring, use the equation shown below. A lot of people panic when they see this, but if we just highlight something, this is LM, LM is here. So what we're saying is E is going to equal 13.7 minus L naught, which we've just worked out here as 5.5 centimeters. And again, you're allowed to use a calculator, show you're working. We might get a method mark if you do. So then, okay, and let me just turn on my calculator. So it's 13.7 minus 5.5, and that is 8.2 centimeters. And the mark scheme says 8.2 centimeters. It says, or correct from candidate's value. So that means if you made a mistake in the measurement, you get a mark carried forward. Then it says here, B, student removes the 200-gram mass from the spring and attaches a stone to the spring and measures the new length of the spring. IA equals 14.2. Calculate the extension A of the spring caused by the stone. Use the equation shown. So in this case, the extension A equals 14.2, because we're going to use that one, 14.2 minus I naught, which was 5.5. That one doesn't change. So again, we're going to just do 14.2 minus 5.5, and that gives us 8.7 centimeters. And again, another mark. Oops, excuse me. Another mark for that. Just dropped my calculator there. Sorry about that. Now it says calculate the mass of the stone M. Calculate the mass M of the stone. Use the equation given. M equals 200 times EA over E. Give your answer to 3 significant figures. So first off, let's do we've got space for our working out here, so we're going to show it. M equals 200 times EA. Well, EA is just here. So 200 times 8.7 divided by E, which is all the way here. We've already worked it out, so we just have to keep track of it. You notice everything's labeled differently as well. Okay, so even the lengths are labeled differently. So E is 8.2. So let's just do that. So it's 200. So 200 times 8.7 divided by 8.2, and that equals. So that equals mass equals 212.195122 grams. Now that is not to 3 significant figures. That is just what my calculator has told me. So I've got to record this to 3 significant figures. So these are the first 3 significant figures. And I can see the following one is 1. So I'm going to ignore all of this. All of these are on my calculator and just look at the first digit here. This is a 1, so I round down. So M is going to be 212 grams to 3 significant figures, like so. I don't know where there we go, 212 grams. So you get a mark for basically the workings out or for getting all of this. If you just put everything like this, you would get just 1 mark, and you get the mark for the appropriate amount of significant figures, okay? Another procedure, wow, the student really loves doing experiments with springs and stones. So the procedure, the student places a beaker of water under the stone, slowly lowers the clamp until the stone is just completely immersed in the water as shown in figure 7.3. And then you can see here, they measure the length LW of the spring. The student's result is shown and the length is 10.7 centimeters. Calculate the extension EW of the spring, use the equation shown. So again, EW, well, we know LW is 10.7, and then we go all the way back to, we go all the way back to the beginning of the question to find L naught, okay? So L naught has not changed. We've still labeled it here. L naught is still 5.5, like so. So again, use a calculator, 10.7 minus 5.5, that equals 5.2 centimeters, like so. So again, I'm not actually doing any maths myself. I'm not having to remember any of the formulas for this. I'm just having to keep a track of all the values I've written down, okay? So just take your time for it and remember that if you see anything here with like little letters in lowercase, that doesn't mean anything other than this is telling us this is the extension when the weight is suspended in water, or like, so the W is for water. This is the length of the spring when it's in water. I naught, normally anything with naught normally means your starting value. So this is the length, L naught, the starting value of the length of the spring. And again, we're going to do the same thing here. For part D, it says use your answers from B, I, and B and C to calculate the density of the stone. So we've got density equals EA. So we're going to go back up to B part I. So it even tells you where to find them. I'm going to go B part I. EA is 8.7. So it's 8.7 divided by, and it's going to be 8.7 minus EW, and that's part C. That's just here, 5.2. That's what density is going to equal, okay? And so if I was doing this in a calculator all in one go, I would do 8.7 divided by, and then I'd open brackets, and then I would write 8.7 minus 5.2, and I would close my brackets there like that. So just make sure you're aware of that. So I've written it out how I would type it into the calculator, 8.7 divided by brackets, 8.7 minus 5.2. And I've got a long answer here. It doesn't worry too much about the marks, but I'm gonna write 2.49 grams per cubic centimeter to keep it to the same number of significant figures, okay, or to keep it to 3 significant figures. So I could either have it that, or they would accept that rounded up to 2.5 grams per cubic centimeter as well. That would give you a mark as well. So then it is important to avoid a line of sight brackets parallax error when measuring the length of a spring. Describe how the student avoids this error. So what they would do is you need to say something like, you need to look at it at the same level as the scale. So a proper way of saying that is to view, and again, view perpendicularly if I spelled that right, yay, perpendicularly to the scale will give you a mark, something like, or any other reasonable suggestion that will give you the mark there. Then it says here, suggest how the reliability of the measurements could be improved. So if you ever see this, think repeat measurements and take an average, like so, okay? And that's your other mark. And then last bit of the question, it says the student decides to check their value for the density D of an irregularly shaped stone by using the mass M calculated in B part 2, and then measuring the volume of the stone, okay? Suggest a piece of apparatus that the student can use to determine the volume of a stone. So you can just say here, measuring, make sure you say that, cylinder. There we go, and that's your mark. You don't need to say how they're going to use it. You just need to say measuring cylinder. And just remember as well, in this case, what's going to happen is you fill it with water to a certain value. Let's say it's 100 milliliters. You place the stone in the measuring cylinder, and the stone will displace or push up water that is in equal volume to the stone. And that's how you would calculate the volume. But that doesn't say that here. It just says what apparatus would you use. So there we go, 20 marks, okay? So if you're not feeling confident with chemistry or biology, or if you're feeling like, if you, like me, have a terrible memory and you're a bit nervous about memorizing food tests and tests for different types of chemicals and things like that, maybe go to the physics questions first. That you don't have to remember anything other than what circuit symbols look like. That's the only thing that we really need to remember here. And sometimes you don't even get a circuit symbol question, okay? But you can see here, this last question was basically just following instructions. So you can see why I call it the insult to your intelligence test, because you just have to follow instructions. And a lot of people think, oh, is that all I have to do? Yeah, don't doubt yourself. If you think that's all you have to do, it might be the case, okay? Make sure you read through every question thoroughly and take your time with the questions. Don't rush into making an answer, okay? Right, everyone, so good luck. Hope everything goes well for the test, for the exam coming up on Wednesday. I'll do another walkthrough for multiple choice paper and for a theory paper as well for physics. Okay, take care, everyone.